Next paper is called Text Entry on Tiny QWERTY Keyboards. It's going to be presented by Leiva, and the co-authors are Alireza Sahami, Alejandro Catala, Niels Henze, and Albrecht Schmidt.
Okay, thank you everyone. I'm Leiva from the Technical University of Valencia, and this work was made in collaboration with the University of Stuttgart, where I was visiting the SIGCHI lab. Let me go quickly with the introduction because we think we are running out of time. Today there are a lot of wearables featuring a touch screen that are becoming widely available to consumers. The point is that these devices can receive a lot of notifications in many forms, but usually there is no direct way of replaying. So text entry on these devices is important simply because space is at a premium. So in fact there are many related words to enter text on these devices. So one approach could be a speech input. However, it doesn't work well in noisy environments. Also, it has some social acceptability and privacy issues, for instance, asking for private data on an overcrowded environment. So another option could be using handwritten input, but it's difficult to see what's written on the screen. Also, because of non-deterministic feedback, same as in a speech input, is prone to recognition errors. So perhaps another option could be using sensor-based approaches, like tilting or clicking on a smartphone, or rotating a wheel to enter some characters, or using mid-air typing. But this technique remains to be further explored and also remain difficult to deploy in practice. Another option would be using pen-based approaches. But in this case, you need an additional device, for instance, an pen, which can be bigger than the actual wearable that the user is interacting with. Another option would be using swipe-based approaches or kind of tabs. For instance, in the paper of Cominos and Dumblo, they use swipes to perform auto-completions, and they deal actually quite well with ambiguous input. Or the swipe board example, which use tabs to select an area of the screen and then additional tabs to select one concrete character. This is target agnostic, and the user can perform eyes-free shorthand input. But I'm sorry to say that in the end, every text entry technique on a touch screen has to compete with QWERTY. So users will only switch and use a different keyboard or technique if it is really easy to learn. And the point is that users are really familiarized with QWERTY. So it's the first keyboard layout for most users. In fact, there are alternative layouts that are optimized for movement efficiency, but users have extensive training with QWERTY keyboards. So let's take a look at a couple of QWERTY-based examples from the research literature. The first one is Minun, as actually a commercial product. It compresses the QWERTY keyboard layout to a single line, and ZoomBoard, which is a multi-tap QWERTY keyboard with visual magnification. And the point is it works really well on coin-sized screens, but it's unclear if it would work well on slightly larger screens. So this is our proposal. It's based on the following design rationale. So a QWERTY keyboard aspect ratio, which is 2:1. The keyboard fits in half of the screen space, so we can use the upper part to display information related to text entry. The point is that different techniques may perform differently depending on the available space on a screen. And in fact, different types of assistance for small queries of keyboard still remain largely unexplored. So here is our proposal. We have two tiny queries of keyboards, where the first one is called callout because it's inspired by the soft keyboards, the callout that is used in current smartphones of keyboard. And the user, when the finger lands on a key, he can refine by slightly moving the finger on the keyboard, and then enter the character by lifting up the fingers. It's a single tap strategy. It has some spatial memory issues because when the finger has landed on the keyboard, it can include most, if not all, the keyboard. So the user has to know how the keys are exactly arranged on the screen. So that's why we create ZShift, which is using the shift pointing technique, and it creates a callout of the key that is going to be entered, but in an unoccluded area of the screen, it's the upper part, and it's using also a slight zoom of the area that is around the key. So it's kind of a motor magnification technique, and it provides a stronger contextual hint for the user. And we in fact evaluated these two techniques and ZoomBoard. So when we quickly jump to the evaluation, in our implementation, the ZoomBoard The source code is publicly available, so we just deploy it on a smartphone. Then we developed the callout and ZShift alternatives. And we included swipe to the right, like in the ZoomBoard prototype, to enter a space, a swipe left to remove the previous character, the tap on the upper part to submit the text, and swipe up or down to change the keyboard layout. But this feature was actually not evaluated, so we just disabled the feature. And we tried 3 different screen sizes. So all of the plans are actually in the paper. The point is that we started with a 1 cent euro coin, which is 3 millimeters smaller than a US penny, and then we slightly increased 1/3 each screen size. So these are the dimensions. So actually what we meant by the small, medium, and large is actually really, really tiny screens. In the experimental setup is more or less the traditional text entry experiment. We tested 3 keyboards by 3 screen sizes, which are 9 conditions. We counterbalance the condition with Latin square design. We recruit 20 participants, and the task is a text copy task using a standard phrasing, and the user has to transcribe some sentences. The phrases were shown at random, and there were no duplicates per participants. Also, the phrases were always visible to the participant, and they were prompted to enter text as quickly and accurately as possible. We have 5 phrases per condition, so 45 phrases per participant and 900 in total, which amounts to roughly 12 hours of typing data. Also, users filled out the system usability scales and the NASA TLS questionnaire after each condition, so they could also have a little break. And this is experimental setup that we use. So actually we attach a smartphone with 2 ribbons to the non-dominant arm of the user, and the strips, in addition to fasten the phone, simulate the edges of a watch and cover the screen so that only a small portion of it is available for interaction. All users use the index finger only, of the dominant hand, and there was a warm-up session before testing each condition. We perform a repeated measure with inserted design with using the MANOVA test because there were dependent variables that are correlated. And then we found significant multivariate effects, so we split the dataset by screen size and performed individual ANOVAs using the Holmboe-Ferroni correction to guard for the type 1 errors. Our analysis include performance, both device-dependent and device-independent measures. I will describe them later. And the usability using the system usability scale and the workload using the NASA TLS questionnaire. So let's go through the results. So first, we look at the words per minute, which is a measure of input speed. And we observed that for the small screen, the callout keyboard performed worse, statistically worse, on the small screen. There were no significant differences between the medium and larger screen. So ZoomBoard seems to perform a little bit better in the medium screen and ZShift in the large screen. Then we look also at the character error rate. So basically the character error rate is imports accuracy. Here we also observed that the callout keyboard performed worse on the small screen. For the other screen there were no statistically significant differences, with ZoomBoard and ZShift performing more or less equally the same. Perhaps ZShift a little bit better in the large screen. Then also we look at the keystroke per character measure, which is a measure of a speed input. It's more or less the cost of entering text. However, it's device dependent. That's why in all conditions we observe that ZoomBoard performed worse than the other keyboards. But it's because ZoomBoard has an innate KSPC of 2 instead of 1. So we looked at device independent measures. So this one, the corrected error rate, is a device-independent measure that allows to compare better cross devices. And here we observe that ZoomBoard actually was more accurate for medium and large screens. So you see that users were accurate while entering text and fixing the errors. Another device-independent measure is the non-corrected error rate, which is kind of an equivalent of the character error rate. And we observe the same result as SER. So no surprise here, the callout keyboard performed worse in the small screen. And the last device-independent measure is correction efficiency, which means the ease with which user corrected the errors. And here we observe that ZoomBoard performed worse on the medium screen, and it's partly because on the smallest screen users were faster and didn't correct many errors. So that's interesting because they just were typing and they was typing at the go, it didn't correct many of the errors. And also fixing an error in our prototypes, in the 3 prototypes, takes only one interaction, which is a swipe to the left. But as in ZoomBoard, the key SPC is 2, that also explains that difference. Then if we look at the usability scores, according to the system usability questionnaire, it's a 10-question questionnaire measured in 1 to 5 Likert scale. So user preferred ZoomBoard for the smallest screen, and there were no clear winner for the medium and large screens. And the word log, measured by the NASA TLX index, here we observe statistically significant differences between the small and medium screens. And in both cases, we observed that callout was not perceived as much useful as ZoomBoard or ZShift. In fact, users felt frustrated with ZoomBoard on the larger screen, but actually there are no statistically significant differences in this case. Then if we look at the short-term learning, so here what we did was average all the trials for all users. So we have 1, 2, 3, 4, and 5th transcribed phrases for each condition and screen. In all cases, we observed that users consistently improved for most of the measure after entering the last phrase, and that was true for all conditions. For instance, this is the word per minute. In the end, user approached the 10 word per minute for the large screen, and for key SPC, for instance, all keyword approaches the innate key SPC. So let me summarize quickly the main implications derived from our findings and this study. So it's kind of a shuffle card. So first of all, the larger the tiny screen, the better. So participants systematically perceive all keyboards being more usable as the screen size increases. But bear in mind that we are dealing here with really small screen. We're talking about 60 millimeter and 32 millimeter for the larger screen. But actually, most touchscreen devices today have touchscreens much larger than this. The second derivation of our findings is that text entry on tiny QWERTY keyboards is feasible. So all approaches reasonably entry speeds with some kind of competitive accuracy, especially for ZoomBoard in the small screen. So I would say that it's actually feasible. And text entry on tiny QWERTY keyboards is not so error prone. So, and surprisingly, the smallest screen was the most error prone, but only 20% of the phrases had some transcription error. So yeah, incorporating error correcting mechanisms is something desirable. In fact, we did that in our workshop paper. You can read more about that. Also, submitting text on tiny screen can be tricky because we showed that in 12 cases out of 900, users tapped on the upper part of the screen while trying to reach a key. So that means that a more elaborate technique should be devised, for instance, using a double tap, just to make sure that the user is not trying to enter text while submitting text. There are some cognitive aspects of text entry on tiny QWERTY keyboards that we should point out. For instance, the callout and ZShift keyboards require the user to relocate the focus of attention, as in touch typing. So once the finger lands on a key, the user has to move eyesight to the upper part of the screen, which could be somehow difficult to begin with. But actually, all users understood all the keyboard techniques. For instance, on the contrary, tap plus zoom interactions as in ZoomBoard are perceived as more easy to learn. However, the ZShift keyboard outperformed ZoomBoard for larger screens in most of the measures. And finally, I would say that there is one QWERTY keyboard for one tiny screen. So for instance, ZoomBoard is a reliable solution for entering text on really small screens, like half an inch. But for larger screens, ZShift seems to be more usable, or at least more likable by our participants. So, yeah, this concludes my talk. I have presented the scalability of 3 QWERTY-based soft keyboards. I have shown that a few millimeters can make a difference, and I have convinced you that the different screen sizes demand different types of assistance. So our research is based on the existing familiarity that computer users have with QWERTY keyboards, which is a well-established property that every soft keyboard has to compete with, for better or worse. Manufacturers can benefit from this finding by selecting an appropriate QWERTY soft keyboard for their devices. And ultimately, this work provides a new understanding of QWERTY soft keyboard design space and its scalability for tiny touch screen. You can download the source code, play with the demos, or read our paper at that URL. So now, I think I'm done on time. Okay. I will be happy to take your questions.
Great. Thank you for a great talk. I'm Sun Jung Kim from KAIST Korea. So first question is how long was the touch that's been taken and the experiment running on a mobile situation or on a stationary situation? Because on a mobile, the tiny screen such as a smartwatch is often texted during the mobile situation, and long corrective movement inside the tiny keyboard is often more vulnerable in the mobile situation. So what was the time and what was the setup?
You mean the timing?
I mean the average touch time during the keystroke.
I think I understand your question.
Yep. So
how long
user need to touch? How long user need to touch the screen for a keystroke?
You mean from in the two conditions that are single
example,
tap approaches, or in all of them? I mean, in ZoomBoard is the first tap zooms in the keyboard, and then a second tap enters the character.
So how much
but
time?
in the other keyboards, the finger first is tapping the keyboard, then the user can move slightly if it's not the key that is shown on the callout, and then they lift up the finger. So you mean the timing between tapping for the first time and lifting the finger in the one single tap conditions, or you mean in all the taps?
So all the taps. ZoomBoard is several distinctive taps and later two conditions, landing and slight movement and takeoff. Am I understand right?
Yeah. So actually, this should be reflected in the words per minute measure, but I don't have the exactly timing between landing the key for the first time and releasing that, but roughly could be 1 second, about, or even less for some conditions. For the larger screen, users were more accurate, so there should be less than 1 second, but for the tiny screen, could be 1 second or more, because all the finger is occluding the screen, so the user could have some trouble by selecting the correct character.
Yeah, so
about 1 second,
like
I would say.
See experiment on a mobile situation, so things getting different, I think. So.
Yeah, agree. Thanks.
Two quick questions. The first is, to some extent, it seems like your results really stem from the fact that you made this design decision to have the keyboard be roughly half the screen. Why did you do that? I mean, considering that, like, if you look at the work that Chris Harrison had done, when they do the zooming, they do it over the keyboard instead of like putting it outside of the keyboard, so that you can actually locate yourself well. And to some extent, like if you look at the small keyboards that are already available on watches, like the Flexi keyboard for Android Wear, they try to use up as much screen real estate as possible. So I don't quite understand why you decided to constrain yourself with this strict design decision that doesn't seem practical.
So first, because the query layout should be shown to the user, because it's the layout that they are mostly familiarized with. So we want to show all the full query layout.
That's not the question. The question is, why didn't you use more of the screen real estate for the keyboard, and so that, you know, maybe you only have like
I think there were only 2 millimeters from the A key to the screen, so it's almost taking all the screen available. But the QWERTY keyboard has a 2:1 aspect ratio, so the wider that you can get the QWERTY keyboard is, we are almost filling up all the space.
Well,
let me show you.
So having shipped a keyboard on a fitness band at Microsoft band, I can tell you that it just doesn't make any sense. Like the design decision that you made, and I just did not understand the rationale.
Actually, because when we were playing with the ZoomBoard prototype, some users felt kind of frustrated when entering text on larger screen. So we thought that why not trying for a one-tap approach, and we were just reproducing the experiment with the same, more or less the same conditions. So if the ZoomBoard keyboard was using half of the space, ours should do. So we decided to use the upper part to display additional information instead of zooming, because that was ZoomBoard was doing. We came up with two different approaches.